Okay, our session is being recorded as always. Welcome to week 7 of our Data610 course. Again, it's a 12-week course, so we're starting sort of the second half. We're into our second major chunk of the course where we're building or thinking about building or starting to build some predictive or at least some models, machine learning models. So I want to remind remind all of you that this is the start of week 7. Your assignment, second assignment, is due at the end, by the end of week 8. So that would be 2 weeks from yesterday. Okay. So that's to clarify. At the end of the week is when that's due. And this is the start of week 7. Next Monday will be the start of week 8. 2 weeks from yesterday will be the end of week 8. So you should be well underway in learning all you can about prediction, looking at various data sets, trying to find a rich one, trying to think about, and again, you may want to use 2 data sets if you can't find a data set where you can build both an unsupervised and a supervised model without straining the way the data set is set up. Remember, what we're doing with unsupervised is we're exploring. We either build a clustering model where things are grouped based on common similarities, or we're building an association model where we say, well, if you bought toilet paper, you probably also bought shampoo. Those are unsupervised. And then, of course, the supervised, we have a wide variety, but mainly in supervised, we build either decision trees, neural nets, or regression, or combinations. Now, tonight, this week is a little bit of a change of pace. I know how hard you all are working learning the software. Anytime you learn new software, for a while it appears very confusing. There's a fog factor that rolls in, and hopefully as you begin to try some of the walkthroughs, as you begin to work on some of the examples and try some things, the fog lifts. And eventually you become a little bit, well, hopefully a lot more comfortable with the software. It's not hard software to use, but any software that's new for the first time requires a learning curve, as you know. So this is a change of pace week. As I mentioned earlier in the course, somewhere in the program we wanted to talk about an optimization tool called genetic programming or evolutionary programming. And the best place to fit that happened to be this week 7 session. So this is something entirely new. Now, you won't have to use this in an assignment. You can just sit back and enjoy and learn about it. And also, it is a very important tool, as I think you'll appreciate by the end of the evening. So I'm going to go ahead and talk a little bit about this part 3. Okay, and then I'm going to give you another briefing, a briefing and a demonstration of the software. So tonight, a little overview, and then we're going to talk about Evolver, different program. Again, you do not have to use it. You could if you wanted to. It's free for 30 days. If you wanted to try it, fine, but it's based on genetic or evolutionary algorithms. Remember the chart that showed sort of the levels of analytics? There's the exploratory level, the visualization level, the predictive level, which is kind of where we're at now. And then there was the optimization level. Well, this is an optimization technique. If any of you are familiar with linear programming, this is a step beyond that, because in linear programming, however great that technique is, and I've taught it for probably 30-some years, it's quite nice, but it did have some serious drawbacks. Mainly, everything had to be linear. And in the real world, hardly anything is. Linear, continuous, non-negative, a lot of constraints, whereas evolutionary algorithm, as you'll see, removes all of those requirements. So I'm going to do a little presentation later on, in a few minutes. Won't be too many slides with this presentation on evolutionary algorithms, and I'm going to do a little demo. Okay? So this is the end of our sort of 3-week segment where we talk about analytic tools, and dealing mostly with prediction, of course. That's the software you're using. But, of course, I'm going to show, as I said, a different one. And then later in the course, we'll get into another program. It's still a third one. Let me mute a couple of people here so make sure we don't have feedback. Okay, let me continue. Now, this is from a company called Palisade. Now, Palisade makes great software. They have Evolver, which is what I'm going to show you tonight. They have a neural network tool, which I use in the MBA program, by the way. They have something called precision tree, which builds a multi-attribute decision tree, a little different kind of decision tree, not really a predictive model. They have a lot of stat tools, and they have something called a ranking tool. So they have a full suite of software, and this is not toy stuff. If you go to their website, you will see that there are many real-world applications of this software, including Evolver. It's much more suitable for like an MBA or a business course because it's not really built for a lot of heavy lifting or building predictive models in the same way that we're doing in this course and, of course, downstream in Data 640. But it does do some things pretty interestingly. And again, you can get it free for 30 days. And we do use it in our MBA program a little bit, use neural tools, and I demonstrate a little bit on Evolver sometimes. All right, excuse me. So tonight I'm just going to focus on that one module, Evolver. Now, I've mentioned this term a couple times, genetic or evolutionary algorithm. What the heck is that? You know, we have a whole spectrum of problems out there and a whole bunch of tools. And so one of the key things a good analyst can do is to match the proper tool to the proper kind of problem. It's not a one hammer for everything kind of world. If you want to solve problems, and I come from a data science background and now in a data analytics background, there are different tools out there. There's queuing theory, linear programming, EOQ, predictive modeling. There's probably 100 or more tools. So matching the right tool for the right problem is really a good first step. This tool, genetic algorithms, is suitable for what we call an NP complete problem. Now, that doesn't mean anything to you right now, but it will once I get through showing and talking a little bit more about it. NP complete, and I'll define that when I get to the next presentation. But NP complete problems basically are problems, just to give you a quick answer or quick definition, problems where there is no model or formula, and the solution space, the possible answers are infinite. So if you have no model to narrow down the solution space to the number of answers that you can check, or no formula to get you to the right answer, and you have an infinite number of possible answers, how do you ever solve that problem? Well, until evolutionary algorithms came along, it was mostly trial and error. There are some interesting case studies available. If you go to this website from the Palisade people, you will see that this software, which costs about $300 to add into Excel, is used by John Deere. It's used by Volvo for scheduling very complex kinds of problems that I'll talk about. It builds an optimization model. You will note that optimization is in quotes because optimization is not really what happens. Maybe near optimization or better than you could do with any other approach would be a better answer. Because if you have an infinite solution space, remember what that means, an infinite number of possible answers. How could you ever be sure that you'd found the best one unless you tested them all? And you can't test an infinite number. A couple of drawbacks in developing models that are suitable for genetic algorithms. One is you have to be able to represent the solution as a chromosome comprised of genes. Each gene represents a variable in the problem, and together a collection of variables with values is called a chromosome. So you can see the genetic part, and I'll explain that more in a minute, does have some carryover, at least term-wise. Then you have to have a fitness function. How well does your chromosome compete in the world? And again, I know this is all very confusing because it's new to most people. We've only had genetic algorithms for about, well, the first theories were developed in the late 70s. And the first software showed up maybe 10 years ago. And the first inexpensive usable software, less than that. Using this Evolver $300 package, airlines and hotels, manufacturing, and you know, if you're familiar with any of these things, job shop scheduling, production, manpower scheduling, inventory management, capacity planning, product mix. These are very difficult problems. In fact, when I got my doctorate, we were told that NP complete, I'm going to define more what that is in a minute, NP complete problems were not solvable. The best you could do was sort of take heuristics, rules of thumb to try to solve them, maybe simulate a small piece. And of course, now we have a different approach. The genetic algorithms do a much better job. You can see some finance applications. You can see some energy applications. You can see some marketing applications and some retail, and there are many more, scheduling and so forth. This is what the opening screen looks like, but I'm going to go ahead and talk a little differently about this. Let me switch over and talk about evolutionary algorithms. Then I'm going to give you a short demo. So right now, I would assume that everybody's still very confused, but I think you'll understand this in a minute. Okay, the reason we call them genetic algorithms is they're based sort of loosely on genetic rules as we understand them, okay? What do we understand about genetics? Well, we understand that for us as humans, we have genes, and when we have children, combination of our genes, right? You get some from mom, some from dad, and they're hybrids. They're different combinations. So in 1975, there were a couple of people working on this kind of idea that said, hey, what if we take these unsolvable problems where we have NP complete. And NP complete, remember, means no formula available and an infinite solution space. So as I said before, if you have no formula you can apply and an infinite number of possible things to try, you can't get there from here because you say, I can't do what we call an exhaustive search. If you have a small solution space, maybe there's only 1,000 possible answers or 1,000,000 possible answers, why not just test them all out, see how they fit? But what if you have an infinite number of possible answers? Where do you stop? And the answer is nobody knows. So John Holland, who came up with this theory in about 1975, 77, said, nature has this problem. Think of a herd of wildebeest out there. Nature doesn't solve the problem of keeping the herd of wildebeest fit and functioning by having a formula. Nature says, I'm going to build a bunch of wildebeest, and they're all going to be slightly different. A little bit taller, some will be a little bit slower, some will have thicker fur, some will have different color fur, whatever, or hair, whatever a wildebeest has. And then I'm going to let them compete. And how do they compete? Well, they compete to avoid getting eaten or sick. They compete to get to the mating grounds in time to pass their genes on. So they compete. And what happens? Well, the fittest ones, meaning the ones that can run the fastest, avoid the hunters, avoid getting sick, avoid getting poisoned, avoid getting shot, avoid falling in holes and breaking legs, and get to the breeding grounds first, pass their genes on. So what happens to herd number 2? Genes. So John Holland observed nature solves the problem where we have a large, very messy problem. What if we tried using some of those same principles to solve these heretofore unsolvable problems? So he came up with this theory of genetic algorithms where he said, let's incorporate some of the things of genetics and see what happens. First of all, we incorporate survival of the fittest. Sorry, I spelled that wrong. Secondly, crossover. What does crossover mean? Well, it means part mom, part dad. So the children, and those of you that have children, know that they're different. They're not all mom, they're not all dad. They get genes from both. What about mutation? I spelled that wrong too. I should run my own spell checker. Occasionally something weird happens. Maybe a member of the herd shows up with green fur. Now, if that mutation is good, meaning it makes that member of the herd harder to spot, harder to shoot, harder to kill, what happens? Well, that member of the herd would get to the breeding grounds and pass on that green gene, and there would be more members in herd number 2 who had green fur. What happens if that mutation is bad? It makes the member of the herd stand out and easier to shoot, easier to kill. Well, then they won't make it to the breeding ground, and the mutation will die out. Same thing as happens with almost all species that have DNA, including humans. Now, you might say, gee, I haven't seen a mutation in a human in a long time. Well, we are losing our wisdom teeth. John Holland said, I bet we could solve some of these unsolvable problems by using some of these features from evolution. Okay, that was his theory. Of course, now we've turned that into software. So let's talk about what kind of problems we're talking about solving. They're called NP-complete. The NP part means non-polynomial, and that means there's no analytical solution procedure available. Now, a queuing, which is a waiting line problem, is, has an infinite number of answers, but it has a formula. There are queuing formulas you can use. So if it has a formula, it doesn't matter if the solution space is infinite, the formula will quickly narrow down to the right answer. Linear programming. The linear programming space that is defined by the constraints is infinite, but the linear programming formulation narrows that down very quickly. But there are many other problems for which we do not have a good analytical formulas. We have none, and they have an infinite number of possible answers. So that's the second part. When I say complete means that there's an infinite or near infinite number of possible solutions. Now let me give you an example. Well, first of all, these are the problem types that this is suitable for. Scheduling. Any of you have scheduling problems? Yes. Did you know that a genetic algorithm scheduling maintenance, which is a very complex thing, capacity planning, inventory management, network design. Most networks are designed by evolutionary algorithms. Portfolio balancing, curve fitting, project management, crashing strategies. Very complex and an infinite number of possibilities. Routing. UPS uses a genetic algorithm to plan its routes for its drivers. Okay. So here's an example problem. This is called the traveling salesman problem. It's one of the classic problems that prior to genetic algorithms was basically unsolvable. Suppose you had to visit 4 cities. Let's say New York, Philadelphia, Los Angeles, and San Francisco. You had to visit those 4 cities and return to where you started. How many possible ways are there to visit the cities? Well, you could start in New York and go to LA and come back to Philly and go to Frisco and come back. Turns out there's n factorial ways to visit the cities. You may remember that word factorial. Somewhere in the 7th or 8th grade, you probably ran into that. But n factorial, any factorial is just, 4 factorial would be 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, etc. So, since we have 4 cities, so we could take a piece of paper and, knowing how far apart the cities were, figure out the best route to travel very quickly by hand. And it says sound is off again, garbled. Well, I hope it's coming back. Thank you. Keep me on track. So it's back. So we could take a piece of paper and figure out by hand the best route to travel. Only 24 of them to check with a little calculator. We can figure that out pretty quick. So this is certainly not an NP-complete problem. Okay, so that was 4 cities. What if we go to 10 cities? Well, there are 10 factorial ways to visit 10 cities. And 10 factorial, as it shows on the screen there, is 3.6 plus million possible paths. It got big in a hurry, didn't it? Went from 24 with 4 cities to 3.6 million plus for 10 cities. Now, that sounds like a lot of paths to check. Certainly couldn't do it by hand, but let's say you had a computer. Any computer today could be easily programmed, and let's assume that it can check 1 million paths per second. Evaluate them and rank them, shortest to longest. So 1 million paths per second. So how long would it take that computer to check every possible path? Well, 4 seconds. We can check 1 million a second. We have less than 4 million paths, 4 seconds. So we can still use what we call exhaustive search. We don't have an algorithm, but we can still just check every possible answer and see which one wins. Not an NP-complete problem, is it? Because NP-complete means no formula and an infinite number of possible answers. Okay, so 4 seconds for 10 cities. Now, what if we say we have 25 cities? Problem gets bigger. 25 factorial is 1.551 times 10 to the 25th. Let's say we still have the computer sitting in front of us, and it can still check 1 million routes a second for the 25 cities. Remember, it's going to check 1 million possible ways to visit those 25 cities per second. What does your intuition say in terms of how long it would take to check all possible routes? So those of you who haven't peeked ahead on the presentation, take a guess. You know, I've had guesses. People say, well, if it took 4 seconds for 10 cities, and I know it's going to take a lot longer, I bet it takes an hour. Other people say, no, I think it would take a day. And some people say, he's trying to trick us. I'm going to say a week. Some people say 2 months. Some people say a year. I don't know if anyone out there wants to hazard a guess who hasn't peeked ahead and doesn't know the answer. But think about it. Intuitively, and it's hard for me to go back and sort of intuitively give an answer because I know the answer, having done this for many years and taught courses in it. Intuitively, if it takes 4 seconds for 10 cities, intuitively, you wouldn't think it would take longer than maybe, I don't know, a month, an hour, a week? Certainly not much longer than that. Well, I'll go to the punchline because if you could look at 1 million routes per second, it would take you over 160 billion years to look at all the routes for 25 cities. I know that's not a typo and not a misprint. 160 billion years to look at all the possible routes that you could have visiting 25 cities, looking at 1 million routes a second. Well, now we have an NP-complete problem because we don't have a formula, remember, for traveling schism problem. And 160 billion years, that's pretty close to infinite. Now, you might be saying, I don't believe this. Well, here's the reference where it came from. And by the way, I will say as an aside, I used to make people, a lot of people used to bet me on this. I've won a lot of money on the idea, but I've decided that's really not fair of me to take your money. So here are the details. If you're wondering how this could possibly be right, go through the math. 25 factorial is 1.55 times 10 to the 25th. If you're checking 1 million routes a second, that's 10 to the 6th. So we divide 1.551 by 10 to the 6th, which means we subtract 6 from the power. So we have 1.55 times 10 to the 19th. There are 31 million seconds in a year. So in 4 billion years, there are 4 times 10 to the 9th times 31.5 million, or 3.155 times 10 to the 16th seconds in 4 billion years. We had 1.55 times 10 to the 19th. So when you divide, in 4 billion years, we would have checked 0.23% of the solution space. Not percent. So to look at all of the solution space would take over 160 billion years. And that's probably why when I was in my doctoral program, I was don't work NP. No one can. Now you can. They've actually solved a 100-city system problem using a genetic algorithm in a reasonable amount of Oh, okay. So now we know there are a lot of problems where genetic algorithms can play. How do we actually do it? Well, let's go through the steps real quick, and then I'll show you a short little demo. The first step, and the choke points, if you will, is you have to be able to represent a solution as a chromosome comprised of genes. Now, remember what a gene is. Each gene is a variable. So in the traveling salesman problem, each city was a gene. And visiting the cities in one particular order, maybe alphabetical or left to right or east coast to west coast, whatever, was a chromosome. Each of those genes can take on several values. Now, in the case of the traveling salesman problem, there's sort of each of those variables can take on one of 25 values. Of course, each gene has to have a separate city, so you have to specify that. So this is one of the choke points. Then what do you do? Well, actually, when you get past step one, you're in pretty good shape. Okay, and I'm going to show you a demo. So then what you do is create the first herd. You say, well, let me just create 20 ways, 50 ways, let's say 50 ways of visiting the cities. I really don't care if they're any good or not. 50 different ways of visiting those 25 cities, 50 different paths. That's all I want. That's my first herd. So that's step two. Then what do? Well, next choke point, remember, is you have to have a fitness measure. Now, for the traveling salesman problem, the fitness measure is pretty easy, isn't it? It's miles traveled. The fewer the miles you traveled in your path, the better member of the herd that is. But that can get messy because maybe you can't go to maybe UPS can't drop things off in Chicago too early in the morning, or maybe there's certain places in the Midwest you can't drop things off, or maybe there's certain restaurants on your route that if you were trying to measure the fitness of the human race, rank us all from 1 to 7 billion, what would be the fitness measure? Would it be looks? Would it be money? Would it be height? Would it be athletic prowess? What would it be? It'd be messy. So sometimes the fitness function is easy to come up with, and sometimes it's pretty tough. But you need a fitness measure. As I said, for the traveling salesman problem, it's an easy one. Miles traveled, as long as we don't add these other constraints, which of course UPS does have, but we don't in the simple problem. So once we've developed a fitness function, we can then take each of those 50 possible members of the herd, and we can give them a number based on how many miles they travel. And we can say, line up, best fitness to worst fitness. Then what do? Well, then we have to get rid of some of the members of the herd. Just like in the real world, some members of the wildebeest herd would not make it, right? Some would get eaten, some would get sick, some would get poisoned, some wouldn't get to the breeding grounds in time. So we do the same thing. We set a cutoff. We say 90% of you get to have children, so to speak. 10% don't, or 80-20, whatever you want to do. Try things. And we also set a small number to mutate, meaning we're going to change certain features of your herd. We might switch Philadelphia and New York. That would be a mutation. So we take one of those answers that survived, and we say, instead of going to Philly first and then New York, go to New York first, then Philly. One switch. That's a mutation. Or if we take two members of the herd and divvy them up in a different way, that's a crossover. And some become extinct. In a lot of ways of determining who gets extinct, but basically the least fit members of the herd become extinct. Then what do? Well, we take the survivors and have them produce herd number 2. And we split their chromosomes, take half the genes from mom, half the genes from dad, or 60% from mom and 40% from dad. A lot of things you can do. And we build herd number 2. And then what do? Repeat the process. We evaluate herd number 2. We get rid of the least fit members of the herd. We build herd number 3, and we keep going until when? Until time runs out. Because with infinite solution space, you can't ever say, I've checked everything. No, it's infinite. But you can't say, gee, I've got 2 hours to come up with a better scheduling idea, or I've got a day to come up with a better traveling route, or in the case of UPS, I've got an hour or 2 to come up with tomorrow's routes and the best way to go. And so, eventually you have to stop the evolutionary process, but it is an iterative process. Think about it, and it's pretty neat. Again, the difficult aspects are representing the solutions as chromosomes, especially if there are multiple criteria. and come up with the appropriate fitness function. Those are the two choke points. Here are some general areas where this has been used. Computer-generated method outperforms human design program for fingerprint improvement. Designing cars, books, and chips. A lot of design. Design has what? Anything that has a large number of variables that can take on a large number of values becomes combinatorially explosive, meaning an almost infinite number of possible answers, and we don't have good algorithms for those. So we do trial and error, or more and more people use evolutionary algorithms. Using artificial intelligence to find biomarkers of calorie restriction. General Electric uses, believe it or not, evolutionary algorithms to design jet engine turbines. They found it outperformed their engineers who've been doing it for 25 plus years. It got a 1% improvement on turbine engines that have been around for years. No one thought you could ever squeeze any more improvements. A lot of variables in a turbine engine. Face prints. Face prints is an interesting one. If you're mugged, there's over 100 cities using face prints. So if you're mugged, they take you downtown. And they say, all right, we've got mug shots. Start looking. Let us know when you find them. And use it. It gives you 16 more. How's the sound? Is it back on? Sarah said, okay, back. So sorry about the sound. I don't know what's going on. Mine seem to be working fine here. So face prints is interesting, and they found you can hone in on the exact perpetrator in about an hour. F-14 systems integration. Imagine scheduling the maintenance for an F-14 with all the myriad of engines and parts and things that have to be checked at different times. Fiber-optic network design. Look at the savings, $1 million to $10 million per design instead of 2-person month, 2-person days. IR target image recognition, outperforming a neural network. Manufacturing schedules. John Deere, company we've all heard of. Volvo, company we've all heard of, use genetic algorithms for optimal production schedules, outperforming humans, and so forth. Army Corps of Engineers looking at using a genetic algorithm to find optimal schedules for the Corps of Engineers to build things. Drawing congressional districts. You can use a GA, a genetic algorithm, to get a more balanced district. An example, a little more detailed on Vimeo. So here's when you open up Evolver. Remember, we've got lots of algorithms. Of course, you've got Insight, and I've got some other stuff. When you open it up, I just wanted to leave it on this opening screen just to show you the variety of problems for which this has been used. I got to move these a little bit so I can scroll down. Okay, there you go. Advertising, choosing the number of ads to maximize exposure. Product mix, delinquent payments, lawnmower production, loading a truck, locating power stations, locating radio towers, et cetera, et cetera, et cetera. These are all NP-complete kinds of problems. And there's a lot of them in the world, which is why evolutionary algorithms are catching on. Okay, I'll move these over just a little bit more so I have more screen. So I'm going to go and open up a file. I hope. Yep, there we go. And explain what this problem is. This is a very simple little demo, but it'll give you an idea. Suppose we have this 50-mile by 50-mile grid where these 12 cities are located. The shaded areas indicate cities with their suburbs. It's just a little graphic to sort of give you an illustration. It has nothing to do with the problem, but it helps to have a little graphic. Here are the 12 cities: Alma, Auburn, Antonino, all the way down to Greenwich, or Greenwich, I guess people say. Here's how many people live in the cities, total of 8,361. Here's where they're located within this grid. So 1743 would be right up about here. So that's probably where Alma is, and so forth. So no big deal here. This is just a spreadsheet. Now, if I go over here to K, oh, I'm sorry. Let me also say we have 3 radio towers, A, B, and C. And they're different size towers, so they have different coverage limits. A has a range of 18 miles, B 10 miles, C 5 miles, just to make it more complicated. Right now, they're all sitting on a truck down here at 000000, right here. There's three of these red dots sitting on top of each other right here. Your job, your task, is to move the towers and place them in the grid in a way that everybody, when the towers are turned on, will hear the radio station. So we'd like all 8,361 people to hear our radio station. So I got to move these towers. So how do we judge how well they're working? Well, this is where the cities are located. Remember, lat long, basically within this grid, really. This, if you click on K, you see a little formula show up here. It says take I4, 17, minus C6, 0, and square it, plus J4, 43, minus D6, and square it. Add those together, take the square root of that. Well, what is that? Well, that's our old buddy, Mr. Hypotenuse. In other words, that is the line of sight between Alma and Tower A. Since all the towers, and then you just copy that formula across. Since all the towers are located in the same place, the answer is the same for all of them, right? So it's 46.24 miles from each of the towers. Then there's an equation here that says if K4 is less than C10, in other words, if K4 is less than 18, put a yes here in N4. Otherwise, that's what a comma means if you've not done many spreadsheets. Otherwise, check and see if L4, 46.24, is less than D10. If it's less than 10, put a yes there because it could hear the signal, right? Otherwise, if that's not true, check and see if M4 is less than E10, less than 5. If it is, put a yes there. If none of those are true, put a no, meaning it can't hear anything. These towers are on right now, but poor folks in Alma are too far away. They can't hear anything. And then you simply copy those formulas. Now, only one town can hear the radio signal, and that's Dobbs. Dobbs can actually hear it from 2 of the 3 towers, can't it? Because 7 is less than 18, 7 is less than 10. You can't hear it from Tower C, but remember, all the towers are sitting right here. So what I'd like to do is move these towers around. Now, I can move them by hand. Let's say I want to put one here at maybe 1542. I'll put A there. I'll type in 1542. So I just moved that red dot right here. Oh, that was a good thing to do. Look, now we got 4,762 people. Assuming I can move these towers fraction of an inch, how many possible locations are there to check? An infinite number. When you hear that word infinite number solutions, what do you start thinking? This could be an NP-complete problem. Do we have a formula that tells you where to put radio towers to get coverage? It's called the coverage problem. No. So it is an NP-complete problem. Now, this is a trivial one because it's very small. So when you have an NP-complete problem, you could be here all day guessing where to put these towers. And this is a simple problem. What if you had 10 towers? What if you had 50 cities? What if you had certain places you couldn't put it because there were ruts or there were streams or something? Very complex. But this is very simple. What is our fitness function? Total listeners. What are we looking at here? One member of the herd. What's his or her chromosome? 000000. We could call them by that name if we wanted to. 0000000. One member of the herd. Well, we want to generate a lot more members of the herd. We want to check and we want to have this thing evolve to a better answer. How do we do it? Well, here's where Evolver comes into play. And it's a very simple program. I love it myself. First, here are the pieces to it. So we go to model definition. Move that over a little bit so we can get a good feel for this. Model definition is pretty simple. I'm sorry, participants in chat, and I have to move you off the screen a little bit there. First of all, we have to say whether we're looking for a minimum, a maximum, or an exact value. You know, if you said, I want the radio signal to be heard by exactly 4,000 people, that'd be the exact value. Or if I want it to be heard by a minimum, well, that's easy. Turn the towers off. But we want a maximum, don't we? So we maximum. Then it says there has to be one cell somewhere in the spreadsheet that tells me how good a member of a herd this member is. Well, here it is, right? It's just right here. 017, one cell. Now, the cell can have very complicated things in it, and I'll say that in a minute, but one cell. So that's all we have to tell it there. We also have to say, are there any limits on things I can adjust? So what cells can I move to get a better answer? Well, you could move all the people, Dobbs, that would get you a better answer. You could move all the cities closer to the towers, that would get you a better answer. You could make the towers more powerful, that would get you a better answer, but none of those are possible in this problem. The only thing we can do is move the towers. So that's what you tell it. You say we can move C6 through D8, this range. And where can I move them to? Can I move them to minus infinity to plus infinity? Because then it's going to take a long time to check. No. We want to move them from 0 to 50 in each direction. In other words, keep them in the square. That's just the limit. You could leave it 0, minus infinity, plus infinity. It would eventually get there, but it would take longer. So I'm giving it some help. So all I've done so far is that first step. Remember, I had to tell it a fitness function, and I had to tell it what things can I change to get other members of the herd. That's all I did there. The next thing you do is some settings. What are settings? Well, first of all, how long do you want this thing to run? You can say, I want you to do a certain number of trials, where a trial is one generation of the herd. So this would be 1,000 herds, 1,000 generations of the herd. No, I don't want that. Or you can say, I want it to run for a certain time, 20 minutes, 50 minutes, 2 days. No, I don't want that. Or I want it to run until the progress. In other words, I don't see a better member of a herd emerge. I don't see a 1% better, then stop. I'm going to turn that off too. Or I could have it run until some complex formula is true. I don't want that. Or I could have it stop if it makes an error. If you leave all of those off, guess what? It won't ever stop until you hit the escape key. Because it doesn't know when to stop. Remember, there's an infinite number. If I'm moving these things a millionth of an inch, there's almost an infinite number of possible locations. What else do I have to tell it? I go to engine. Random number seed. You see, I'm playing God here. I'm starting the herd. I'm starting the world, okay? I've taught courses in genetic algorithms as part of an artificial intelligence course where we were all running this software. And I gave much more complex problems. And we all had the same problem. And I gave them each a different initial seed. Well, that's like, let's say 20 students in the class, 20 different gods starting their worlds at different places. They will evolve differently because they start with a different random number seed to get the first herd. And after that, it all takes place automatically. So you can actually have, for a reasonably complex problem, you can have, if you have a 20-person class, you could get 20 different answers after running it for 10 minutes, 15 minutes, an hour. Kind of funny, isn't it? So what do you do in the real world? How do you know you started with the right random number seed? The answer is you don't. You may want to run your scheduling problem or your routing problem or your location problem like this many times with different random number seeds just to see if you get better answers. Because remember, if you start your herd at a different evolutionary point, it will evolve differently. If you want everybody to start and get the same exact answer, they all have to put in the same initial seed for a random number. Isn't that neat? And it's going to use a genetic algorithm. And how many members will there be in each herd? 50. Want some diversity, so 50 is a good number. How many members of the herd will survive and get to create the next herd? Half. How many members of the herd, remember there's 50, so 25 of them are going to produce the next 50. How many members of the herd will mutate, meaning have some change? Now, mutation could be just swapping your X and Y coordinates. Wouldn't make any difference on this one, but it would if this was 20 and this was 10. Next member of the herd, I make this 10, make this 20. 10%. Isn't that neat? I think it is. You could say, what do you want to see on the screen? I say, well, show me the best member of the herd. Every time you find a new best, put that member on the screen. Because I can only see one member of the herd at a time on the screen. I can't see all 50 of them. I'm looking at one member of the herd. I want to see the best member. And then you can run some macros at the start if you need to get your data set up. But that's about it. So I said, okay. Believe it or not, we're done. Now, this is such a small problem that when I hit start, it says, all right, I'm getting ready to go. Here's my progress. I'm going to stop it right away. Herds, 73 iterations of the herd, 73 generations. It started at 1625. The best it's found so far is 5,038. I don't want 5,038. I want 8361. So let me run some more. Of course, this is a small problem. It runs for rather quickly. It got to 8335 in less than 10 seconds. Now, I've used the same problem for probably 10 years that I've been teaching genetic algorithms. I've let it run as long as 5 hours on this little trivial problem. I have never been able to get above 8335. So that means one of two things. It's impossible to get to 8335. In other words, it's impossible to get everybody to hear the radio signal towers. And look where they've been moved to. Here's where they're at. Okay, it's impossible to get poured over into the solution. Okay, that's one possibility. It could be that it's impossible. There is no solution that gets all 8361. Or the other alternative is I just haven't stumbled across it yet. My herd hasn't evolved enough times to find that missing answer. I don't know which of those is true. Okay, again, this is why with an evolutionary algorithm, you can never say, I'm done. Now, if I get an 8361, I can say I'm done because I can't do any better than that. But as long as I don't get 8361, I can never say I'm done unless every possible solution is checked. And there's a near infinite number of possible solutions, so I'm never going to be done. So I can let this run. We've now run for a minute and a half, and we've gotten about 14,000 generations of the herd, and we've not found anything better than 8335. But that's a pretty good answer. That is everybody except these 26 souls in Dover. And you can see now we know exactly where to put the radio towers. We put A at 23.9, 24.1. We put B at 00, leave it where it is. And we put C at 13.3, 43.5. Pretty slick. Now think about this. It's a large problem. And you're trying to cover a battlefield with different kinds of antennas and different kinds of towers and trying to optimize the signal so the troops could hear it. This is a very reasonable approach. Okay, I'm going to go ahead and stop it because I don't think it's going to get any better. Let's say I've run it for 6 hours. Well, let me let it run for a second. I'll tell you a quick story. I built a genetic algorithm model for optimizing a advertising problem, a real-world kind of problem. I presented it at the Research Society of America conference. I had run it for 8 or 10 hours, written my paper. It was a very complex solution fitness function that I had embedded in a cell. I had run it for 6 or 8 hours. I went into the presentation. I turned on my computer like this, brought the problem up, and I said, well, let me just let it run while I explain my problem. I know it's not going to get a better answer. 10 minutes into my explanation of what I had done, guess what? They all started pointing at the screen and hooting and hollering. I turned around, and yes, it had found a better answer. Even though I had run it for 6 hours, I hadn't found a better answer. When I started with a different random number seed, it did find a better answer. And, of course, I had to rewrite the paper. So that could happen here. You might stumble across something that gets 8361. I don't think so, but let's go ahead and stop it. So I'll stop it. And when you stop it, it says you want to stop because remember, I didn't give it any criteria for stopping. So I got to tell it to stop. So I got to hit that stop button. And then you can go do things. You can look at the summary, how many trials it ran, when it found the best answer. You can look at the log of what was going on. You can look at the population, the diversity, the stopping options, the summary, the progress. This shows you that after a few trials, it got to 83, 65, and then about 30,000 trials later, it hadn't done any better. I don't think it was going to. And I can say, okay. Okay, so now I have an answer. All right, so now that's one solution. I want to do one more little example. Suppose that the owner of the radio station lives in Dover. And she says, you know, with those towers, I want you to get as many people to hear the station as possible, but I have got to hear it, and I live in Dover. Well, we know this isn't going to hack it because the people in Dover can't hear it. So, So what are we going to do? Well, let me just open a different file. Whoops, sorry. Let me just go to my recent files and open one here. This looks like the same problem, doesn't it? Same number of people, same locations. Our boss, the owner, says, I live in Dover. I got to hear it. Does that mean we got to can the whole problem and start over? No. I'm going to go to the settings. I'm going to go to the model definition, rather. And I'm going to make one subtle change. I'm going to say we still want a maximum, but you'll notice that the optimization cell is this cell, not this cell. This cell. It's the only change I made, really. So let me say, okay. And what's in this cell? Well, I put a formula in this cell. Very simple formula. It says if O13 is greater than 0. Now, where's O13? Aha, it's right here, isn't it? If O13 is greater than 0, then take the number in O17 and put it here. Otherwise, that's what the comma means. Otherwise, leave this to 0. So the only way you get an answer here that's not 0 is when there's something in this cell, meaning Dover can hear the signal. That's the only change I made. So this no longer becomes the fitness function. This does. And the only way this gets a good value is if there's something in Dover. So now when I run it, you will see that all of the answers include Dover. Otherwise, you don't get points, do you? It'd be a 0 there. This is the thing we're looking for. This is the thing we're trying to optimize. The only way this gets a number is if there's a number here. If there's a number here, then this number comes down to here, and this is the thing we're trying to optimize. So the computer's working hard. You'll also notice that we're not getting that 8335, are we? No. We're missing all those poor souls in Carthage, right? Well, so there was a detriment. The best answer was leave Dover out. When we said got to have Dover, we lost Carthage for the moment. I'm going to let this run because I've had answers where Carthage was in it, but someone else was out. I won't tell you whom because things can change, again, depending on the random number. So now we've run about 9,000 generations of the herd. The best answer we've found is 7671. However, I think if I let this run maybe a minute and a half or a couple of minutes, and I can't guarantee this because every time I started, I let it pick an automatic random number seed on its own. I can't guarantee that, but I know I've had better answers where Carthage was in, and I think maybe someone else was out. I'm not sure who at the moment. The ideal thing, of course, would be everybody. And just like before, I can't say that there isn't a solution where you can put those towers and everybody will hear it. But it also could be that there isn't anything better than 7671. That's a pretty good answer, right? We're only missing one city, poor Carthage, located at 827. So right up in here, they can't hear anything. But again, you're not going to be able to move those towers by hand and get a better answer. I can assure you that. I've had students, I can do better by hand. I say, go ahead, I'll give you 20 minutes, and I'll buy you lunch if you come up with a better answer by hand than this thing does. Remember the guidance, you have to include Dover. No one's ever been able to do it. UPS has a similar challenge. They challenge any of their route persons, men or women, if they can come up with an improvement to the routing that the genetic algorithm generates, they get a big bonus. For UPS, if they can save 1 minute per truck per day, it adds up to millions of dollars over the course of a year. So I saw a riveting presentation from the UPS guy who put this all together, but basically is pretty impressive. Well, maybe we can't do any better than Carthage, okay? I thought there was a better answer, but I've let this run almost 3 minutes. We've done 25,000 generations of the herd, and we've not gotten anything better. So we could let it run longer, or you can go try it yourself. Download the software. This is one of the sample problems. I've amended it slightly to make it more usable in class as a short demo. But I think, the trade-off here is that when we forced to include Dover, because the boss lives there, then, okay, we lost somewhere else. And what we lost was the 690 souls in Carthage. Now, if you said I got to have Carthage, you could make that complicated. You can make the formula that goes in here very complicated. Very complicated. Multi-attribute, multi-formulas, all that can be summed up everywhere in the program as long as there's one cell somewhere that is the bottom line cell to look at. So again, I'm going to stop it at 4 minutes because that's about all the time we need to let it run for tonight. Almost up with our hour class time. Because I want to say a few more minutes, more things about genetic algorithms. So we've let it run. Again, we can tell the boss, hey, we were getting 8335 people covered, but we weren't covering you. If we have to cover you, then the poor souls in Carthage aren't going to hear the radio signal unless you want to make the towers more powerful or add a fourth tower. Yes, there's other things you could do, but it ain't going to happen. But what this is doing is a very efficient, sort of like human nature, generating iteration after iteration, generation after generation, mutating. Remember, every one of these trials has 50 members. You're only seeing the best. 50 members. Behind the scenes, we are getting rid of half of them. They're having the other half cross-split their genes and create new members for the next herd. We're taking 10% of the 50 or 5 and having them mutate, meaning maybe we swap an X and Y. You can control how that's done a little bit if you'd like in some of the programs. There's another good program that I use sometimes called Gene Hunter. About the same, looks about the same, costs about the same from Word Systems. Okay, so I'm going to go ahead and stop it. We're not getting any better tonight. So stop optimization, and there we go. And again, if you look at the summary, look at the progress, you can see it went up, blip, 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 and then it leveled off. Okay. So we have our answer. We can say, boss, if you want to hear it, we're going to lose Carthage, but everybody else can hear the signal. All right. All right, let me go back to my, I'll close the spreadsheet. I'll save that. Save that. And we'll go back to wherever we were here. What happened to my, there we go. So, I was talking about a lot of the possible applications. There are voluminous numbers, and what's interesting is, of course, we don't really have any other potential ways to solve these problems. So this has been a giant breakthrough. Now, you're not going to find a lot of applications. There are some at my website. Remember, if you go to steveknoop.com and look under news links and look under genetic algorithms, I try to capture whenever I see one. Because they do occur. There's still not a lot of people who are familiar enough and understand what's going on enough to really use this technology, but it's interesting, and it's an optimization technique, sort of, okay? Okay. The station 00 doesn't sound like a good answer. How is the starting population generated? Okay, well, we have access to the model. A couple of good questions. You remember that random number seed is what triggers the internal generation of just 50 members of the herd. We don't really care if they're any good or not. Okay, so every time you use a different random number seed, you're going to get a different world. You're going to start the evolutionary process with a different setup of first solutions. And it evolves from there based on the rules I told you. Another question was, do we have access to this model? Well, you can go watch this again or my Vimeo presentation. You can also go to Palisade, download the trial version, which is good for 30 days of Evolver or of all of the package, all of the modules. And one of the sample ones is the location problem. I've modified it slightly, but it's in there, very similar. And there's other ones too. There's a product mix, a routing problem, a machine scheduling problem, several great examples. So you do have access to it, sort of. I mean, you do for 30 days if you download the software. And it's a great package if you have this kind of problem. So this was just an opportunity to give you a little taste for an optimization technique that is sort of in the field of analytics. I mean, it deals with a specific kind of problem, not a predictive model, not anything like that. It's an optimization model. Okay, so back to what are you going to do week 7 and 8? Well, week 7 is your final week to really master, so to speak, or at least master to a certain level, the prediction software. And of course, week 8, at the end of week 8, you will be turning in your second assignment. And I tried to give you some guidance in the first one. Make sure that you explain your data set. Make sure that you build some good models to compare them on the appropriate accuracy. You always want to have a training and test set for a supervised model, of course. You don't have to use the same data set for both of your models. If you have a data set that lends itself to both, that's fine, but most data sets are better suited for one approach or the other, supervised or unsupervised. You can usually turn a supervised data set into an unsupervised by just ignoring the target and doing some clustering or something. But you can use 2 data sets if you choose. Okay. And then week 8, while you're busy finishing your assignment, in other words, the lecture material for next week, I'll be talking about decision management systems. That's where we get into the third third of our course, which is, okay, once you've framed a problem, once you've built a model, then what do? Well, you got to sell the answer. You got to get it operationalized. You got to turn it into something that's usable in the organization. It doesn't do any good to say, look at this really neat predictive model. Somebody says, well, how do I use a neural net, or how do I use a regression equation, or what do I do with the decision tree? You have to be able to articulate that. So the data scientist is becoming more and more linked to the business model. And that's what we're going to talk about with decision management, where you manage the decisions that you're going to make as a result of having built a good predictive model. And that's where Mr. Taylor's book comes in. Remember, he wrote this book, one of our textbooks. Okay, so as always, we have the final slide which says if you have any other questions you feel like you must ask right now. Anybody who wants more information on genetic algorithms, I'd be glad to send more links. Just send me an email, more information, more readings if you want to do more. During the week, of course, we have the Let Me Have Any Questions discussion area for questions where the answer would be beneficial for all to see. And of course, we have personal email to me or a phone call for any kind of events that you think need to be handled that way. Emergencies can be handled with a phone call. Personal questions or items, email.